Now we see that now we see that now we see that now we see that is 0 less or equal to phi n and phi n is less or equal to phi k, phi n less or equal to phi k, because this n it's greater or equal to k and phi is decreasing, so we can therefore phi n is less or equal to phi k, and that's equal to phi k into the into characteristic function of ek, characteristic function of ek. It's ek here. Okay, ek is already defined. Characteristic function of ek, characteristic function of ek union b minus ek. Okay, that's equal to phi k into characteristic function of ek plus phi k into characteristic function of b minus ek. Sorry, it's ek here, not ex, ek. Ek. Okay. So this one, it's but this phi k, it's phi 1 is less or equal to m, therefore phi k is also less or equal to, which is less or equal to m times characteristic function of ek, because as phi 1 is as phi 1 is less or equal to, it's ek, as phi 1 is less or equal to m, therefore phi k is also less or equal to m, plus phi k times characteristic function of, I can write it as whole b, because chi of b minus ek will be less or equal to chi of b, as b minus ek is subset of b. So now we apply the integral throughout, this will give, this gives 0 less or equal to m times integral of chi of ek plus okay, this one actually here this phi k on uh, on b minus ek, phi k is less or equal to epsilon. Okay, it's less or equal to, it's less than epsilon, phi k, sorry, less or equal to epsilon. Okay, so on b minus ek, this phi k is less or equal to epsilon, and phi k is less or equal to m throughout for each x. Okay, but on this particular set b minus ek, it's less or equal to epsilon. Now we apply the integration. This 0 less or equal to m times m is a constant number. It will be m times the integral of chi of ek plus epsilon times the integral of this function chi of b. Okay. So this implies 0 less or equal to 0 less or equal to epsilon times uh, this mu of ek is mu of ek is less or equal to epsilon. Okay, this m times epsilon m, or you can say m times epsilon plus it will be strictly less, not less or equal to, it's strictly less. Okay, m times epsilon plus the second term, that's equal to epsilon times mu star of b, because uh, or I want to add one more step here. This is this is less or equal 0 less or equal to m times mu star of e key, because this integral of chi of e k is equal to mu star of e k. Okay. Now this one, this implies 0 less or equal to m times, this is epsilon less than epsilon, strictly less than epsilon, right, plus epsilon times mu star of b. So that's equal to epsilon times m plus mu star of b. Okay. This is true for all n greater or equal to k. So letting this n approaching to infinity, we will see that this is actually integral of phi. In fact, integral of phi. This is actually integral of phi, and like to write here, it's actually integral of phi. And here, integral of phi. On this side, we have integral of phi, and that's positive. Integral of phi and integral of phi, and so this means letting n approaching to infinity, letting n approaching to infinity, we get limit of integral of phi n is equal to 0, because epsilon will approach to 0. So this means integral of phi n, it will decrease to 0. Actually, it will decrease to 0. Decrease because limit is 0, and this is a decreasing, so again decreases to 0. Decrease to 0. Okay. Now we prove the next part in which phi is a step function. That's the second part of this theorem. Now if phi is a step function, such that phi n increases to phi. This implies minus times phi n decreases to minus phi. So which implies minus phi n plus phi decreases to 0, which implies the integral minus times integral of phi n. I have also the linear property integral of minus phi n plus phi, which is equal to minus times integral of phi n plus integral of phi, decrease to 0 by the previous part. So whenever we have a secant which decreases to 0, secant of step functions, then the integral will also decrease to 0. So this will give minus times integral of phi n increases to, or you can say decrease, not increase, it is decreasing here, decreases to decreases to minus times integral of phi. So that implies the integral of phi n will increase to integral of phi. So this proves the second part. Now in the next theorem we'll show that if we have a two sequences of step functions converging to the same limit function, then in the limit of the integral of both the step functions will be the same. So that's the theorem here. Let phi n and psi n be two step functions. As we can switch function, let phi n and psi n be two sequences of step functions, of step functions, and f is a function from x to r star. Okay, r star means the extended real valued function. Be given is a function be a function such that it's a function, be a function such that this phi n increases to f and psi n also increases to f. Then the integral, then this is a very important theorem, then this limit of integral of phi n is same as limit of integral of psi n. If phi n and psi n are two step functions, we can substep functions such that both converging to the same limit function f. Then limit of the integral of phi n and the limit of the integral of psi n will be the same. So clearly this f is a measurable function because phi n is a step function and step functions are measurable functions, and the limit of a measurable sequence of measurable functions is again a measurable function. So therefore this f is measurable. Proof. The limits may be infinite as well, but in any case they are equal actually. So limit of integral of phi and the limit of integral of psi may be infinite. Now this f is a measurable function. So clearly f is a measurable function. That's there is no need to prove this. Clearly f is a measurable function. So now for each fixed m, now for each fixed m is fixed, okay? M is fixed. For each fixed m, we have this the meet of phi m and psi n. The meet we have meet of phi m and psi n. This psi n, it increases to f, so this will increase to phi m meet f. Okay, this limit is with respect to n. Phi m is fixed. Okay, this m is fixed. Psi n increases to f, therefore phi m meet psi n will increase to phi m meet f. Phi m meet f, and that is equal to, what's the meet of these two functions? Since we know that this phi increases to f, this phi increases to f, so that means phi m is always less or equal to f. So it's always, so this meet will be phi m. It will be phi. So this is a phi almost everywhere. This limit is actually almost everywhere. Okay, this is, it should be, this is almost everywhere here. Okay, in the statement of the theorem, that this convergence is almost everywhere. Okay, so let's see this. Now why this meet is phi m? Because as phi m is increasing sequence and its limit is f, so this means phi m is less or equal to f for all m, for all, and so this is the reason. This is always less or equal to f, so that means their meet, their minimum value will be equal to f. Now next we'll see that this limit, this increases to, okay, now we have to apply the previous term. This can substitute function is increasing to phi m, so let's apply the previous term with respect to m, because this limit is with respect to m. So this implies limit and approach to infinity integral of phi m meet psi n is equal to integral of phi m. Okay, they just apply the previous theorem. So let's name it 1. Name it 1. Now again we have this again this one phi m meet psi n phi m meet psi n is always less or equal to phi m as well as psi n. So in particular, it's less or equal to psi n. So this is almost everywhere because you are taking the meat of these two functions, and this is true for all m. For all m, this is true. Phi meet psi n is always less or equal to phi m because you are on this side you are taking minimum of these two. So minimum of these two will be less or equal to phi m as well as psi n. So in particular, it is less or equal to psi n for all m and n also. For all m and n. Now let's apply again the integral. What's this integral? So now this integral, as already done, this integral of phi of m, which is equal to limit of integral of phi m meet psi n. That's already done. Phi m meet psi n, but this phi m meet psi n, it's less or equal to psi n, so it will be less or equal to, this limit is here, this will be less or equal to, so limit and approach to infinity integral of psi n. Okay, because this part, this meet is less or equal to psi, so we have to apply the monotone property of the integral. That's already done. So this is true for all m. For all m greater or equal to 1. So now letting m approaching to infinity, we get limit of integral of phi m is less or equal to limit of integral of psi. So similarly, we can on similar lines, limit and approach to infinity integral of psi n is less or equal to limit m approach to infinity integral of phi. So combining these two inequality, we get limit and approach to infinity integral of phi n is same as limit and approach to infinity integral of psi. So whether you take m approach to infinity phi m or n approaches to infinity psi n, they are same. There is no difference between these two. So hence the theorem follows. Hence the theorem follows. Hence the theorem follows. So now we have one more theorem here that gives the integral of a limit of a sequence of step function in terms of the measure of a set. So the theorem is let phi n be a sequence of step functions. Let phi n be a sequence of step functions. Let phi n be a sequence of step functions if a is a subset of x, it's any subset of x, such that phi n increases to characteristic function of a, then a is measurable set, then a is measurable set, and limit of integral of phi n is equal to mu star of a. It's equal to mu star of a. Proof. So look at this. This limit of phi n is chi of a. Therefore, chi of a is measurable function because it's the limit of the sequence of measurable functions. So since Since chi A is a measurable function, therefore A is a measurable set. A is a measurable set, as we know that, the reason is that as we know that this the characteristic function of a set chi of A is measurable if and only if E is measurable. So because we know that chi of E is measurable if and only if E is measurable, and here chi of A is a measurable function, therefore A is a measurable set. A is a measurable set. Okay. A is a measurable set. This is done. Also, we can assume that because here the limit is not everywhere. It's this is almost everywhere in the statement. But we can assume that also we can assume that also we can assume that phi n x increases to chi a of x for all x in x. So this is already explained in one of our previous theorem. So here I don't need to explain it again. So we can assume that this convergence is everywhere. Now for each n, let's define the set an for each n. For each n, define an which is equal to the set x belongs to x, such that this phi n x is positive, where this the value of the function is positive. Then this an is measurable as phi n is measurable. Then an is measurable. Then an is measurable for all n greater or equal to 1 as phi n is measurable. As phi n is measurable for all n greater or equal to 1. Okay. And this an and this is increasing, so you can say an is subset of an plus 1. This you need to verify. This union an is equal to A. So you verify this yourself. Okay, this is verified. So this is very simple. An is increasing, so you can subsets, and this union an is equal to A. This you need to verify. This one is simple, because whenever phi n is greater than 0, then phi n plus 1 is also greater than 0, as phi n is increasing. So that's trivial. But this union is equal to an. So if x is in union an, then x is in sum an. Whenever x is in sum an, that means about that an phi n of x is positive. Phi n of x is positive, and here limit of phi n x is equal to chi x. But phi n of x is positive for some n, say for some k, then phi n of x will be positive for each n greater or equal to k. So if phi k of x is positive, suppose phi k of x is positive. So here I want to prove this inclusion. This union is subset of A. Okay. So let us choose any x in this union. Then x is in some a k. Okay. Let me explain it here. Then x is in some a k. So whenever x is in a k, it means that phi k of x is positive. So if phi k of x is positive, it means that phi n of x is positive for all n greater or equal to k, because phi n is greater or equal to phi k for n greater or equal to k, as phi n is an increasing sequence. So whenever phi n is positive for all n greater or equal to k, then its limit must be positive, but its limit is chi a of x. So that means chi a of x must be positive. But chi of x has only two values, 0 or 1. Since it's positive, therefore value must be equal to 1. So whenever chi of x is 1, it means that x must be in A. So that's this side. Okay. This inclusion, this union is subset of A. And the reverse is trivial. Whenever x is in A, so it means that x belongs to some A, obviously, because whenever x is in a, then chi of x is positive, it's equal to 1. Then x must be in some an. For if possible, x is not in any an, x is not in any an. So if x is not in any an, then phi n of x will be less or equal to 0 for each n. So if phi n of x is less or equal to 0 for each n, then its limit is also less or equal to 0. But its limit is chi a of x, which is equal to 1. So that means 0 is less or equal to 1, which is a contradiction. So this is actually true. This union is equal to a. So it's an increasing sequence and union is a. Therefore, I can write this as, so this implies this a, and it increases to a. That's the notation actually. A n increases to a, and it follows that chi of a n will also increase to chi of a. Also, this also it's given that phi n increases to chi of a. So these two sequence of step functions chi a n and phi n, their limit is the same. And now we apply the previous theorem. Limit of the integral of chi a n is same as limit of the integral of phi n. So therefore, by previous theorem, therefore limit of integral of phi n is equal to limit of integral of chi of a n. Limit of integral of chi of a n. Okay. So this limit is equal to limit of chi of a n. But this one, what's integral of chi of a n? It's the measure. This is equal to limit n approach to infinity integral of chi n a of this is equal to mu star of a n. But this a n, it increases to a, therefore mu star of a n will increase to mu star of a. So this limit is actually mu star of a. So on this side, it's actually the limit of integral of phi. That proves this theorem. Now we close this section by proving the following theorem. That's the last theorem of this section. The simple and step functions and their integrals. This one is the last theorem. Let f from x to r, let f from x to r be a measurable function, be a measurable function satisfying fx greater or equal to 0, satisfying fx greater or equal to 0 for all x belongs to x. Okay, then there exists a sequence of simple functions, then there exists a sequence phi n of step function of simple function, not step functions, of simple functions such that this sequence is non-negative, such that 0 less or equal to phi n, and this sequence increases to f for all x in x on x. Okay, on x. So given any measurable function, non-negative measurable function, we can always find the sequence phi n of step function, simple function is such that that sequence is non-negative, and this sequence is also monotonic increasing, and the limit of the sequence is equal to f. Okay, so let's we try to define that sequence of step function which is monotonic increasing, and the limit of the sequence is equal to f. Okay, so first of all we define sets for each n. Let a and I is equal to, for each n let this a and I is the set x belongs to x, such that I minus 1 times 2 power minus n, I minus 1 times 2 power minus n less or equal to f of x less than I times 2 power minus n. This is our set a and I. Okay, and I is varying from I is equal to 1 up to n into 2 power n. Okay, n into 2 power n. This I varies from 1 to n into 2 power n. Say for n equal to 3, this I varies from 1 to 3 into 2 power 3. 3 into 2 power 3 means 3 into 8, that's 24. So I varies from 1 to 24 in that case, if n is equal to 3. Okay, then we note that then we verify, then we first verify that, we first verify that they are disjoint with respect to I. A and I intersection A and J is phi for I not equal to J, where I and J varies from 1 to n into 2 power n. So first we verify this. So let's assume on contrary, assume on contrary, and take some point in the intersection and take this x belongs to A and I, and x belongs to A and J, where I is not equal to J. So whenever x belongs to A and I, it means that this I minus 1 times 2 power minus n less or equal to f of x less than I times 2 power minus n. And on this side, when x is in A and J, it means that j minus 1 into 2 power minus n less or equal to fx and less than j times 2 power minus n. Now, since I is not equal to j, so we can assume that this I is strictly less than j. So that means I is less or equal to j minus 1. Okay? If I is strictly less than j, it means that I is less or equal to j minus 1. So, okay, now let's look at this. Now here, this f of x, it's less than I times 2 power minus n, but this I is less or equal to j minus 1. It's less or equal to j minus 1 into 2 power minus n, but j minus 1 into 2 power minus, it's less or equal to fx. So it means that fx is strictly less than fx. A contradiction. A contradiction. So therefore they are disjoint. Therefore A and I intersection A and J is phi for I not equal to J. For I not equal to J. Now for each and we define these step functions. First we note that each A and I is measurable. We note that each A and I is measurable as f is measurable, because each A and I is actually the inverse image of this set. Okay, inverse image of semi-closed interval I minus 1 2 power minus n to I 2 power minus n. So inverse image of this semi-closed interval is always a measurable set whenever the function is measurable, and here the function is measurable. Okay, so this A and I is measurable as f is measurable for each n and I. Okay, so let's define for each n, let's define this phi n. Let's define the function phi n, which is equal to I runs from 1 to n into 2 power n and into 2 power n, 2 power minus n into I minus 1 times the characteristic function of a and I. This sum is with respect to I. Okay. Then these finds, they are simple functions. Then phi is a sequence of simple functions. Then phi n is a sequence of phi n is a sequence of simple functions. Is a sequence of simple functions. Is a sequence of simple functions and and this is and they are also non-negative. You can easily verify they are non-negative, and 0 is less or equal to phi and phi is less or equal to phi n plus 1. They are monotonic increasing, and each phi n is less or equal to f. Okay, this is true for at any point x, actually, for all x in x. Okay, this monotonic increasing part I will leave it for you as an exercise. It's monotonic increasing, but this one is trivial. This phi n x is less or equal to fx, because whenever say x is in some a and I, then its value is 2 power minus n times I minus 1. But 2 power minus n times I minus 1 is less or equal to fx. So whenever x is in certain a and I, then the value of the phi n x will be equal to 2 power minus n times I minus 1, but 2 power minus n times I minus 1, because whenever x is in a and I, then 2 power minus n times I minus 1 is less or equal to fx. So that means phi n x is less or equal to fx. And if x is not in any a and I, then its value is 0, and but fx is a non-negative function, then again this 0 is less or equal to fx. So for each x belongs to x, phi n x is always less or equal to fx. So that's trivial. And this one I will leave this one as an exercise for you. Okay, this is monotonic increasing sequence. Now here I want to explain I will find that for each fixed x, let x be any point of x. Okay, now look at this for a fixed and what are those intervals actually for fixed and. So for fixed and where the following interval is for I varies from n to 2 power minus n. For I equal to 1, the interval is we have these intervals actually 2 power, because this 2 power minus n of I minus 1 is less or equal to fx, and fx is less than. Okay, so on it's so we have these intervals actually. On this side it's closed. Okay, so we have these intervals where fx lies actually for this x belongs to a and I. We have this interval is I minus 1 times 2 power minus n less or equal to x and less than this one. Okay, where I is varying from 1 to so on up to n into 2 power n. Okay, this one. So if I varies these, I will get the following. We'll get the following intervals. For I equal to 1, it will be 0 to 2 power minus n. So we have the following sequence of intervals: 0 okay, 0 to 2 power minus n. Okay, the next for I equal to 2, say it I minus 1, that's 1 into 2 power minus n times into 2i is 2 power minus n. Okay, and similarly we have 2i is 2 power minus n. The interval is here actually to 3 times 2 power minus n. And if we continue this process, at the last step we have the value of I is at the last step the value of I is what's the value of I at the end of the step? I varies from n into 2 power n. So last value is n into 2 power n. For I equal to n into 2 power n, the last interval is like this it's I minus 1, I is equal to n into 2 power minus n minus 1 into 2 power minus n and n into 2 power n into 2 power minus n. Okay, so this is not here minus, here it's sorry, it's okay, it's here 2 power n. So this interval, last interval, it's equal to so I'm multiplying this by, it's equal to it will be n, okay, minus 2 power minus n, and this will be just n. So if I choose any fixed x, so if x is very close to 0, then it may lie in this interval maybe. But if x is very large number, then I have to choose n so large such that x lies in this interval. Okay. So what I mean to say that for any fixed x, I can find n sufficiently large such that x belongs to one of these intervals. Such that x belongs to one of these intervals. So for a fixed x, belongs to x, for fixed x belongs to x, this difference I will say 0 less or equal to fx minus phi of x, because x belongs to some interval, some set, some interval for sufficiently large n, not for small n, because for small n is say n is equal to 10, I have this 10 minus 2 power minus 10 to 10 interval. This is the end point is at 10. So this is lie on this interval, say this point to 10. Okay. So this is say 10 minus 2 power minus 10. But if x is equal to say 11, say 12, so I have to choose different n. So for any x, I can choose n so large such that x belongs to one of these intervals. Okay, so it may be the last interval or maybe the between any interval is but for choosing x so large, for choosing n so large, this x must belong to one of the intervals. Okay. So for fixed x belongs to x, we have 0 less or equal to fx and fx minus phi n x, because this phi n x, it increases to fx, so fx is less or equal to phi n x. This phi n x is less or equal to fx, it's already done phi n x, so this is non-negative number, and this difference is less or equal to 2 power minus n, because whenever you set x is in some interval, then you have to say a and I, say x is in some a and I. So whenever x is in some a and I, you'll see. So now I will a little bit explain it here. For any x in x, for any fixed x in x, we choose n so large such that x belongs to a and I for some I equal to 1, 2, so on up to n into 2 power n. Okay, so if x belongs to a and I, so it means that we have this fx minus phi of x. What's this fx? This fx is less or equal to I times 2 power minus n. That's the definition, because x is in a and I, so fx less than this. It is in fact strictly less than so minus phi x. So let's see the definition of phi. Okay, let's see the definition of phi here. What's the definition of phi? Phi is this x in a and I. So that means of the value of phi n will be equal to 2 power minus n times I minus 1, because x is in a and I. It is just in the one set, so it is in a and I. So at this ith stage, its value is 1, and this will be equal to 2 power minus n times I minus 1, and the rest of the terms of this sum will be equal to 0. So I would say this So let me erase it here because this is okay. So we have this 0 less or equal to uh, we have this 0 less or equal to fx minus phi n x, and x is a and I. This fx less or equal to I times 2 power minus n minus this one. It is less or equal to it's equal to I minus 1 times 2 power minus n, and that's equal to I times 2 power minus n and minus I times 2 power minus, they will go, it's just 2 power minus n. So letting n approach, because n is sufficiently large, so letting n approach to infinity, we get this phi n x approach to fx as n approach to infinity. So this, but phi is increasing sequence and its limit is fx. So that means phi n x increases to fx. It's true for each x because x was chosen arbitrary point in the space x. Okay, so that phi n x, it increases to fx. This completes the proof of the theorem. So this theorem precisely states that given a measurable function which is non-negative, we can always find the secant of step function. Secant of simple function is which is monotonic increasing and converging to that function, that measurable function. That's why in the one of my early lecture, I told you that these simple and step function, they are actually building blocks for the uh, for this measurable function is an integrable function, is because for any non-negative measure, I can generate that non-negative measurable function with the help of simple function. That's in this theorem actually. So in the next lecture we will see this. We will see that actually in our earlier lectures we have shown that this major space this R with Lebesgue major lambda and S as summing, where this S is equal to the collection of semi-closed intervals. This we have shown that A and B belongs to R. This we have shown that this is a major space where this Lebesgue major is defined by on this semi-ring, it's equal to B minus A. This is major space. This we have shown. Now in next lecture we will extend this notion of major to Rn. So we'll show that Rn is major with the Lebesgue major lambda n and the semi-ring Sn. So here Lebesgue major, what's this Lebesgue major lambda n is actually here. This Sn is actually this. It's the n dimension. It's like this Cartesian product of n semi-closed intervals. Okay, where these AIs and BIs, they are in R. So this Cartesian product of n semi-closed intervals, it's subset of Rn. So this is the collection of subsets of Rn actually, and we will see that this collection is a semi. This is already done actually. This collection is a semi-ring. Now we define a set function on this collection by A and Bn, which is equal to B1 minus A1 into Bn minus An. So this product of these lengths. And Lebesgue major lambda n. So it's just a notation lambda n actually. So I will write this notation here. It's not lambda power n. So I will write this as lambda n. Okay. It is just the notation for the n-dimensional. Lebesgue major are n-dimensional. Okay, and Lebesgue this lambda n of phi, if this interval is a phi set, then I will take the value equal to 0, and if this is non-empty set, then I will take its value is equal to product of the lengths actually. And we'll see that this set function on Sn is actually a major, and that is we show that actually this Rn lambda n and Sn is a major space, is a major. That we'll do in the next lecture, and we'll use this theory of integration on simple and step functions to prove this result. This is a major space. Thank you.